Thank you very much, Matt. Ah. All right. Well, it's great to be here. Great to have a good crowd. We're going to talk a little bit tonight about an idea that I actually got out of a magazine. I want to give Anthony Williams credit for that. Those of you who don't know who Anthony Williams is, he's the author of I think it's called C++ Concurrency in Action. It is a book written specifically about the new multi-threaded standard library for C++ 11, which he also implemented his own version of called Just Software. So he's in England. He has never spoken in the United States before, but he's going to be at CPPCon this September, and it may be the only opportunity that people in this country have without going over to England to hear him speak. So I'm very excited to have him there. And I saw this article he wrote in Overload magazine, which is the basis of what I want to talk about tonight. I've enhanced it a little bit, mostly to make it fill an hour. But anyway, so I want to start out in a way that he didn't start out at all. So we're kind of off in another area. And I want you to look at these things and think about these things and see if somebody can tell me, what do these things have in common? Explicit constructors, modern casts, specifically const cast and static cast, explicit conversion functions, and this uniform initialization, and particularly the narrowing conversion part of this. Anybody have an idea about what these things have in common? Steve, what do these have in common? All right, so Steve's here to keep me on the straight and narrow. Yeah, Zoltan, did you have an idea? It's type safety, yeah. Essentially, what they have in common is that they actually make it harder to do conversions, right? Because these kinds of conversions may actually be problematic. In other words, the lesson that we've learned in C++ with the many years that we've had C++ is that very easy, and that is implicit casting. When you don't have to do anything at all to say you want to cast, you just say, well, here's this thing, and the type that it wants to be is over here, and the compiler just magically says, oh, I can convert this to this. And it sounds so convenient. It's such a good idea. Or as Steve and I were talking about some of the early C++ features, he said it's a good idea at the time, makes sense, right? But what we find out over time is that very often that cast happens when you didn't intend it to. And you know, the convenience feature, while it's very nice and very often nice and convenient, it doesn't make up for the fact that sometimes we have bugs, which are more than just inconvenient, right? I mean, they're wasteful, they're expensive, they're frustrating, and so we want to kind of do that. So the trend in the standard is away from implicit casts toward explicit casts. Now, that doesn't mean that the existing implicit casts are going to go away, right? Because that's we aren't trying to break backward code. What we're trying to do is when we introduce new features, we're trying to say they're not going to have implicit casts. Any casting about the new feature is going to be explicit. And so, so we're going to talk tonight about enums. And before we get to the C++ 11 or the modern enums, let's talk about classic enums. These are some of the things that are kind of annoying about them. One is that the size of an enum is not specified. Now, we don't often think about that because the way we use enums, we generally, maybe it's not that important how much memory they take out, but there are cases where it becomes important. We are going to have a large number of classes that have a large number of members that are enums, and we would like to be able to control the size one way or another. And the standard has always just said the compiler is going to pick a size for the enum that it likes. And maybe your compiler is looking for performance, and it may not pick the smallest possible enum. Or maybe your compiler is looking to save memory, and it may not pick the fastest possible enum, and you have no say either way. Proper scoping rules is not respected. And what does that mean? That means that what we would like to have is something like this, where I say, oh, here's my enum called values, and it's got a couple of values in it. And I would like to say that when I access those values, I say values : first. I use the scope resolution operator. Because in C++, that's how we refer to things, right? If something's in a namespace and we want to refer to the thing in the namespace, we say namespace name : And if it's in a class, we say the name of the class : That's how we specify things that are in braces. And here's this thing in braces, but that's not the way it works, right? Because this has to be backwards compatible. It was developed for C. C didn't have a namespace a scope resolution operator. And so that's how it works. You would declare an enum and then whatever you declared in the enum was in the global namespace. And that's just the way it works. I'm sorry, say that again? Oh, well, yeah. We assume A value has already been declared in some way. My point is not the A value. My point is that the values equal first. That we want to express an enum in our set of enums, a particular value. We would like to be able to say that that's the scope of that. And one of the problems that we have is that enums can collide. We may have two different sets of enums. We may have something about pay, which is low and high, and something about altitude, which is low and high. And then you may have a collision because there's no way to differentiate this low from this low. So we introduce a solution to that. Oh, I'm sorry. And then the other kind of annoyance here is, and this is one of the ones that's very important to us, is that classic enums become ints or convert from ints or other enums without implicitly, right? We don't have to explicitly do any explicit casting. We just implicitly say, oh, here's this int, I want to assign it to something that's of type enum, or here's this enum and I want to assign it to something of type int, or I want to perform some kind of operation that's only available for integers, and it converts both enums to integers, and then, so all those things are convenient and wonderful, and we like them, except when they introduce a bug, which they very often do because of this very easy implicit casting. So this is error prone. We don't like that. So C++11 introduced this some new features for enums. One is that there's this concept of the underlying type. So this new syntax allows us now to say enum values colon, and then some kind of integral value, integral type, and then we list the actual enum specifier. And so what we're saying here is that I want the compiler to use an integer size object. I want a data type of integer to be used to hold my enum value. So the size of this enum, which before in C++, it was possible in C or C++ to say size of enum and find what the size is, but there was no way to specify what that size would be. And the compiler could in fact use different sizes for different enums. If you had an enum that only had a few values, then the compiler might pick a smaller size, but an enum with a larger set of values, it would have to have a larger size. So this is optional. Obviously, if we made it not optional, then all our old code would just break because existing enums don't work that way. And it's also possible now that we have this new thing from the standard library where we can say underline type of whatever enum we want, colon type. And then this type specifies what the underlying type is. And so we can use that in generic code if we're dealing with enums. And we say, oh, this is an enum. Well, what is the underlying type? We can use that type declaration, type function. Yes. If it was up here, it'd be int, and down here, it will return whatever the size or whatever the underlying type is, but there's no guarantee what that is in a portable way. One compiler could say, well, it's going to be an int. Another might say it's a short or something like that. All right, so the underlying type is selected by the compiler, and it's not portable. And what I mean is the code is portable from machine to machine, but the understanding of what the underlying type is not portable. A different compiler on the same machine or a different version of the same compiler, all of these could pick a different underlying type. So there's a new thing also introduced in C++11, and that is something called enum struct. And you can also say enum class, but I prefer enum struct. But you say enum struct, and when you do that, the word struct is telling the compiler that you would like to be able to use the proper scoping. So you can say enum struct values first and second. And when you do this, when you want to refer to first or second, you do use the syntax we talked about earlier. You'd say values colon first or values colon second. It now has the proper scoping that we as C++ programmers would expect. Yes? There's no difference in this case. Unlike when we declare a struct or a class, there is no difference here. They're completely interchangeable here. There's no difference. Good. That's a good question. What's that? In this case, we're not specifying the underlying type. The difference is that with the new, I think I'll bring it up in the slide, but with the new syntax, if you don't specify what the underlying type is, the compiler is required to make it int. So that is the difference between the new version and the old version. So if you just willy-nilly go into your existing code and say, oh, I'm going to make all the existing enums into enum struct, then you'd have to change all your code to do reference to those enums. And I'm not saying that would be an awful thing, but if you did it, then all those enums would suddenly be ints. And so you might have some memory increase in size if you use a lot of ints and the compiler is choosing a smaller value for an enum. Right? So the compiler is required, unless you say otherwise, with the enum struct to use int. But you can also specify anything else. The underlying type is the same logic for the new enum struct as the new enum. One of the things different about the new enums is there's no implicit casting to int or other enums. So this is why we've been talking about and building up to this idea that you can't just automatically cast an enum to an int and back and forth if you're using the new modern enum, which we like to use. We'd like to be able to use it because it has better scoping rules. I know of one really interesting situation where it actually makes sense to use the older syntax. But almost always, I mean, I'll be using the new syntax because I like the scoping rules. I like the fact that when I refer to an int, I say this is, you know, values : int or whatever the type is. All right, yay! We're not going to have this implicit casting anymore. Great. So one of the things that we do with classic C++ enums is we use them as bitfields. So what we're talking about there is the ability to choose values for the enums. Notice it makes sense that I go first and second, that's 1 and 2, but why is third 4 instead of 3? 2 to the third, right? What I'm doing is I'm picking values such that each enum actually represents a separate bit, right? So first represents the first bit, second represents the second bit, and third represents the third bit. And what is the value when everything is 0 except the third bit? 4, right? And the nice thing about this is that if I give you any particular number, you can tell all the different enums that went into making it up, right? So if I gave you the number 7, you would say, oh, well, that has to be first, second, and third all set. That's how bitfields work, right? And so we do this sometimes with classics. And that allows us to do something like this. So here's my function, and it takes some options. And the options are these enum set, right? And I'm going to call that, and I'm going to say, I want first or third. And that's not logical OR, that's bitwise OR. And so what that's saying is that I want the first bit set and the third bit set. So what is that value? It's 5, right? 1 and 4. That's 5. But what happens is inside the function, I'll know that the user called this function and which options do they want? Well, they wanted the first option and they wanted the third option. Of course, I mean, this would represent something more useful in some way. I mean, not just the first option, second option. If you were drawing a window, the first one being set might say, oh, I want a close box. And the second one might say, I want a size box. Whatever options we would like to specify. And this works not because enum allows for this kind of operation, because it doesn't. There is no bitwise ORing of enums. It's not supported. The reason it works is because this code is actually converting the enums into integers, performing the operation, and then converting them back to int. Right? Because that's what the compiler does. Whenever you tell the compiler, I want to do some operation, and the compiler says, well, that operation is not defined, before it gives you an error, it says, well, could I convert these things into something where it is defined? And the answer is yes. It can convert these things into something where that makes sense. It converts them both to ints, and then it has an int result. And then with some func, it's saying, oh, you're calling some func with an integer, but you don't have a sum func that takes an integer, but you do have sum func that takes this enum. So I'll convert the integer into an enum. So that all works. And we might think that what that means is that enums support these operations, but they don't. It's the integers that do. And this implicit conversion makes this possible. So the thing is, this is really kind of nice to be able to do. And if you introduce the new modern enums that don't automatically convert to ints, then can you do this? Well, sure. You can cast them to ints and then do the operation and cast them back. Who wants to do that? I'm not seeing a lot of hands here, right? So I think you guys are on board with me that it's kind of cool to do, but it's something we can't do, right? It also means that we can do this. We can take the first option and multiply by the third and divide by the second. What does that mean? What? It's nonsense. Logically, that has no meaning. I mean, yes, you could look at the math of it, but if you're thinking of these as bits, it makes sense to do logical ands and logical ors and do a mask and those kinds of things, but it doesn't make sense to do these kinds of things. And yet, that will compile, because the compiler has no problem at all at saying, oh, can I multiply two enums together? No, but I can convert them to ints first and multiply them. So it can do that, but it's not really what we want it to do. So we can't do it with this new, where we say options, with the new options, we couldn't do this at all. That won't compile. That's good, makes us smile. But unfortunately, the old stuff that we wanted to be able to do, the bit mapping stuff, we can't do that either. And so that's not good. So we can fix this though, right? It's C++, there's a fix for everything. Before we do that, I want to talk a little bit about standard launch. Standard launch is this scoped enum. That's what we call this, scoped enum. And it's defined in the standards to support this, because this is exactly the kind of thing you'd want to do. So this standard launch async and standard launch deferred are enums that are defined that you can pass to the async call. What does the async call do? Yeah. Kicks off a thread and returns a future, right? Except it doesn't necessarily kick off a thread. By default, it does, because by default, we're going to have async. But it's also possible, if you wanted to, you could say, oh, do a deferred, which is to say, don't kick off a thread, wait and execute it when I want the answer. Don't do it on a separate thread. Defer the result until I'm ready for the answer, right? It's also possible, and this is the standard specifically calls this out and says, if you want, you can specify that the compiler can choose, or the library can choose. So you give us both values, and then the library will make the appropriate selection of what will be done. And the way you do that is by ORing the options together. And how does that work? Because we just got through saying that that wouldn't work. Well, the reason it works is because the standard has defined that these operations are available on this particular enum set, and so they have defined that. They have created operator overloads for that. Does that make sense? Right? And we can do the same thing, right? If I have my bitfields and or my enums and I want them treated like a bitfield, I can do the same thing. I can go in and create operator overloads for my enums to support being able to do bitwise anding, oring, whatever, inverting, all these kind of operations, exclusive OR. I can do all those things, right? But that's a little tedious, particularly if I have lots of enums that I want to do. I mean, what do we do when we have lots of things that we want to apply the same code to in C++? What do we do? What do we... Okay, that's not the answer I was looking for, but the answer I was looking for, of course, is template. We have something we want to do to a lot of different types, and it's the same thing over and over. We create a template, right? Okay, so here's this template for some enum. We're going to have operator. I hope you can see that. That's vertical bar operator, right? So we're doing a bitwise OR, not a logical OR, but a bitwise OR operation. And so just for ease of use, I'm going to make a type def, which in C++ type defs are spelled using. So I'm going to define this underline type, which is equal to type name, std underline type of E type, right? So that's the underlying type of whatever the enum is. And that doesn't matter if the enum, if the user specified the enum or the user let the compiler choose, which the compiler will always choose on a modern enum, the compiler will always choose int. But whatever it is, this will tell us that. And so all we're doing now is what I said before, which is how we could do this, right? We will cast, do a static cast of our enum into whatever the underlying type is, do the logical OR against the underlying type cast of the right-hand side, and then we return casted back. Okay? Make sense? Problem solved? No? What? Technically, what's not okay is to have enums such that the enum values that are greater than the range specified. If all you're doing is ORing things together, then you're going to be safe. Technically, you could have something that exceeds, for example, in the example that we were talking about earlier, where I said we had first, second, and fourth. If you ORed them all together, you have 7, which is outside the range. Technically, that's not right, but it's never going to bite you because there's no way that the compiler is going to create a type that will give you 3.5 bits. It's not, you're either going to get all 3 bits or you're not. Yes, it's 2.5 bits or whatever. Right? So that won't bite you. There are some things you could do that might, but I think we're safe on safe ground here. So we'll assume this is in some appropriate namespace because I don't ever want to put anything in the global namespace except what I absolutely have to put in the global namespace. What do I absolutely have to put in the global namespace? One thing, it has to go in the global namespace. What is it? Main, of course. Main has to go in the global namespace. All right. So, oh, wait a minute. Something's wrong with this operator. What's wrong with this code? What's wrong with this code? Yeah. It's incredibly greedy. That's not what I was thinking about, but that's true. That's the problem we're going to solve later. But I had a more immediate thought on this one. But you're right, Zoltan. Anybody else have ideas about why is this written wrong? What's wrong with this code? Yeah. Underline has to be an integral type. When you specify the enum, the requirement is that you can't make up, like you can't say underline type is a string, which, yeah. Well, that's what he was saying, that depending on what the underlying type is, or may not actually be defined, but I think it always will be because the underlying type has to be integral. So it will. Right, but or will never be more bits than what the underlying type can support. Right? Right, but it's still the same number of bits. It's not overflowing bits. It's still only 3 bits. 7 is the highest number you could get that way, and it's still only 3 bits. Yes, but the range is from the lowest one is 1, the largest one is 4, and so the compiler is going to have to use something that's at least 4 bits inside, or 3 bits inside. So, yeah. Well, but the underlying type is going to have to be the same. I mean, it's the underlying type, so we're safe there. Yeah, go ahead. That's not what I was looking at. We did say it's in namespace, but we'll talk about that later. Yes, Steve. Const expert. That's right, Steve. I gotta give you a book. Oh, that's the wrong answer. Const expert we're going to get to later. You know the answer now to the next question. This question is, we always define operators in terms of their assignment operator, right? DRY. What's DRY? What? Can you say that again? One more time, Jim. Sorry, Jim. I got to go for that, right? So we say don't repeat yourself. Well, what's the problem here? Well, the problem is that we always define operators in terms of the assignment operator, right? Because whatever the implementation is, we don't want to have to write it twice. Also, we want to make certain it's the exact same implementation. For a user-defined class, you really hate it if an operation, say plus, actually logically was different than plus equal, right? That would be a problem. And so we always define plus in terms of plus equal. And in this case, going back here, the bitwise OR should be defined in terms of bitwise OR equal to make absolutely certain that we don't have any bugs. And if we fix a bug in one, we fix them in both, right? So we want to be consistent. So anyway, here's the rule. Always define operators in terms of their assignment operator. So we should define this operator in terms of the OR equal. Okay, so what would OR equal look like then? Why not define the operator OR equal in terms of the operator OR? I think I got a typo there. It should be in types of, yeah, no, here we go. Operator, it's broke. There's the problem. OR equal. All right, why not this way? Why don't I define this one, the one that we've talked about, the operator OR? Why not, why are we having to define it in terms of OR equal? Why not define, this is a typo, right? Because this should be operator, same one. Yeah, the other way around. Why not define OR equal in terms of just OR? So assume the equal sign's not there. That would fix the slide. Okay. Now that we fixed the slide, now we have to answer the question. Why is it? Yes. Because of temporaries, yes. It is absolutely necessary that that OR equal will do less work than OR, right? Because the OR equal is doing something in place. The OR has to create and return a temporary, right? So it must do more work. So we want to define the one that does less work as the base one, and then define the one that must do more work as essentially creating a temporary and then applying the equal one. Right? That's for efficiency. Yes. Correctness, it could be done the other way around. But correctness, you could do them independently too. So, so this is our implementation of OR equal. It's not really very much different. It's just that we want to do this in place, right? That's the whole point of the OR equal. So we're going to static cast this not to the underlying type, but to a reference to the underlying type. Okay. How's this? This fix it? Yes. The return value? You're absolutely right. That should, yes, there's a bug there. Yeah, that's definitely a bug. Is that what you were going to say, Steve? Yeah. That's actually not the compile error that I was thinking of. It won't compile. And why won't it compile? The reason it won't compile is because you cannot do this reference cast of an enum to its underlying type because they're considered unrelated types. Now I get to do this little segue. When I was at the standards meeting last year at Kona, I got to witness what was this absolutely delightful, in a perverse sort of way, discussion where there was a particular proposal that had been made where the proposer was saying he would like to have, I don't want to say who it is, but I did give away that it's a guy. There's like one woman in the standards committee, so it's not her, it's someone else. He had this proposal, and what he wanted to do was he wanted to be able to implicitly cast scoped enums, not to integers generally, but he said that that it should always be able to implicitly cast to its underlying type. He said this cannot cause any loss of information, right? Because it is the underlying type to begin with. The only thing you're doing is you're telling the compiler, you know, you've got this enum thing that is a particular value of a particular underlying type. I want you to forget that it's an enum and just think of it as the underlying type. And that implicit cast should be valid. And the reason the proposer was bringing this up was because in his company's code base, people were starting to use modern compilers, they were using this, and they needed to be able to do, for one reason or another, they needed to be able to do this conversion of enums into their underlying type. And they were having to call static cast. They were having to do this static cast. And in his company, a static cast was a huge no-no. And so all the code reviews would get bogged up on this because I don't know what the entire thing was, but I think if you actually used a static cast and tried to check it into the repository, you had to sacrifice a chicken or something. I don't know what it was, but it was a big deal, right? And the argument was, this doesn't make any sense because this is always safe by definition. And the reason it was so much fun to watch this is because he had taken this to, you guys don't know all about the whole standards committee organization, so I'll briefly tell you. What I'm about to tell you is for language. There's a parallel of everything I'm about to say also for library. There's a library working group and a library evolution group, and there's also a language working group and a language evolution group. And the job of the evolution group is to figure out at the high level what new features are. You go in and you present. And he had gone into the evolution group and he presented this, and the evolution group said, fine, that's an okay feature. Then you have to go to the library working group, or in this case, the language working group. And the language working group, we call them core. These guys are amazing. They understand C++ at a really low level. These are the compiler guys that really understand what the standard's supposed to say and what it's supposed to mean. And so after you get the general evolution committee to buy off on something, then you take it to the core group and you say, here's the wording I came up with. How does the wording need to be changed so that it says what I mean instead of what I'm saying? And I just happen to be in the core group because I'm not one of those guys, but they're fun to watch, although it's interesting to watch because they're all sitting and staring at their computers. And then every once in a while, someone will say, uh-oh, well, that's a bug. It's amazing to watch these things. A lot of fun. So I'm sitting in there watching, and here comes the fellow with his proposal. And almost immediately, one of the guys in the core looks at this and says, well, this example you have in your paper, motivating example, he said, you realize that in this case here, that would be undefined behavior, whether we take your position or not. And he kind of looked at it and said, oh, no, I guess that's true, but I don't care about that situation. I just want my feature. And so they end up discussing the feature a little bit, and it turns out that core does not like this feature. Core thinks it's unsafe. And in fact, they pointed out that there are times when, if we do this, there are times when you wouldn't have to do a cast where the unscoped, the old-fashioned C versions of enums would actually have required a cast. So there are these kind of scary situations where, so anyway, the fun part about the whole thing was that he got very irate, and he said, look, evolution has bought off on the feature. You don't get to tell them that they can't have the feature. You just have to tell me how to word it. And the head of the core group said, I'm sorry, we are allowed to kick it back if we feel like we found a bug in their proposal. And so it was just fun to watch, right? Two nerds testosteroning out over this. The thing is, I wasn't very sympathetic to the proposal. I thought, you know, you need to figure out why static cast is such an awful thing, and then make that work in your process. The bug is in your process. The bug's not in the language. But now I suddenly feel some love for him because I'm saying, why can't I cast a reference to the underlying type of the enum with a static cast? Because it's the same thing, but it won't let me do that. So I can't do that. Instead, I just cheat and I say, okay, fine. We will just do a regular equals, and it ends up copying instead of doing in place. And of course, for an integral type, this is so not inefficient, right? I mean, it's not as theoretically efficient as you would want. You would want to do it in place, but for an integral type, this is probably done in a register anyway, and so it's probably not that expensive. Okay, so now, Steve, what's wrong with this? What's wrong with this template? Okay, spending too much time on it. What's wrong with it is that if it can be expert, const expert, we'll make it const expert. So now we make it const expert, okay? Okay, so now how do we implement the original operator now that we have the or equals? Yeah. Yes, it does. We talked about it. Yeah, yeah. You guys on top of things, right? Yes, this should be returning a reference because that's what the left-hand side is, and in fact, it should be that. What's that? In the parameter list? What have I done now? The right-hand side be a reference? You could make it a const reference. I don't see what that's going to buy you, though, given that it's an integral type, right? Yeah. Yeah. I don't think that one needs to be a reference. What's that? Yes, because that could in fact be a char or something very small, and making it a pointer might actually make it bigger, because that's what a reference would imply, right? It actually would be passed by pointer somehow. Yeah, Steve. Yes, that's the problem, is that I should be returning, well, I'm returning left-hand side, that's the right thing to do. It's just that it should be referenced rather than by value. Yeah, absolutely. Yes, we'll have to fix that one. Okay, so now we have implemented OR in terms of OR equals, and of course, it's trivial. Once you have OR equals done right, then doing the OR is right. So now all we have to do is repeat this for all our other things. So we need to do AND equals so that we can do AND, exclusive OR equals so we can do exclusive OR, and then just do a twiddle. Okay? Okay, so we've made it as a template. The pros are 7 short templates allow us to treat any enum like a bitfield. Any enum. And you don't have to rewrite this for every enum you want. You just, boom. All our enums now bitfield. The cons are, we may not want to treat all enums like bitfield. So we've been talking about the examples that we've given, the launch async, and also the example that I gave you, they make sense as as bitfield. But not all enums do make sense as bitfield. There are times when the enums just represent, specific values, and they're not meant to be ANDed and ORed together. So we may not want that. Furthermore, this will potentially clash with overloads of operators, such as standard async. Because the standard has already said that async supports these operators. Now we've written a new template that's going to use that. Of course, if this is not written as a template, then that would probably win, but there is the potential of having this overload. But the other one is the one that, didn't you say this, Zoltan, that it's too greedy? Yeah, it's too greedy. For example, this would now match, because all we did was we took a template of 2 things, and we said I want to be able to OR them together. This doesn't make any sense. Now, is that going to actually compile? Why wouldn't it compile? If we applied this to our template. Right, because the compiler's going to choke and say, wait a minute, there is no underlying type for string. So it wouldn't compile, but of course any user that did this is going to get this really cryptic, there's no underlying type for this type, and the user's going to say, what? Where did this come from? Right? So how do we make it so that we can use our template, but only use it when we want to use it and not use it when we don't want to use it? SFINAE to the rescue. How many of you think SFINAE sounds Italian? I just heard that today for the first time. Seriously? Nobody thinks that's Italian? SFINAE. SFINAE. Now it sounds Italian. All right. Substitution failure is not an error. This was a term coined by Van der Voort and Jositis, and it's like so many C++ terms. It just rolls off the tongue. It's just this delightful, easy acronym that makes so much sense. What it's saying is, and it applies only where type deduction can take place, and type deduction only takes place, template type deduction only takes place where there's function templates, not type templates. So if you have a templated struct, there's no type deduction. Now that, in 17, that's going to be there's an asterisk there, it'll be a little bit different. But in general, even then, that's not really going to be the situation. So in the situation where you have a template, or maybe multiple templates, and the compiler is trying to deduce what the parameters to the template would be, given the parameters that you actually call. So in other words, the scenario is that someone's calling a function. It has to be a function. and they've called this function foo, and they pass some parameters to foo. And the compiler is saying, oh, here's a foo, it's a template. And then it has to figure out, well, given these parameters, what are the template parameters that this particular function template would have to have in order to be useful? If this is the best match, what are the types? And it turns out that in some situations, it doesn't make any sense. There's no possible definition of the template types that would make sense with the particular parameters you pass. And if that's the case, instead of having the compiler throw up its hands and say, wait, I can't compile because I can't perform this substitution, what the compiler does is say, oh, I'm not going to choke on this. I'm just going to ignore this template because it obviously, it doesn't substitute properly. It fails to substitute. And we're not going to say it's an error. We're not going to stop compiling. We're just going to throw out this particular template. And we're still going to look for other possible matches, other foos in this example, right? Other functions that could be called. So if substituting the template parameters into the function declaration fails to produce a valid declaration, in other words, taking the template, the parameters that you've passed in your code, and trying to substitute those into the template declaration, if that fails to produce a valid declaration, then the template is removed from the function overload set. This foo doesn't count. I'm going to look for other foos, but not this one. So it's removed from the function overload set without causing a compilation. That's what SFINAE means. Now, that doesn't seem very helpful to what we're trying to do, but it turns out it's the key to solving this problem. So, because we're going to create a constrained template. And a constrained template is simply any template where we are deliberately constraining, deliberately limiting the situations where it can be applied. And the way we're going to do that is by using SFINAE or something else. In this case, we will use SFINAE. There are a number of ways of creating this, but there's something in C++ 11 that came via Boost called enable if. And what that does is it allows us to very easily SFINAE out templates that we don't want to apply in a specific situation. So here's how enable if could be implemented. There's a base template which takes some kind of Boolean. Now notice that's not a type parameter, that's a non-type parameter. It's a Boolean. It's either something that evaluates the compile time to true or something that evaluates the compile time to false. That's a Boolean. And then there's a class, and the class has a default, but probably we won't be using that. But what we have is some struct, templated structs, templated on these types, called enable if. And notice the base definition is just an empty struct, nothing there. But we specialize it for the true case, right? So here's the true case. The true case, we're saying struct enable if in the true case, and then we define this type def t of this type. This t is type def. I should have used using here, shouldn't I? But anyway, we're declaring that type def means t in the case where it's true. What is the value of type, this name type, when it's true? It's t. What is the value when it's false? There is no value. And that actually is the key. What is the type of t in the false case? That's the secret, is that in the false case, it doesn't make any sense. In other words, any expression that uses enable if we evaluate it to false, the compiler is going to ignore that template and say this template cannot apply to the function you're trying to call. It is not going to be there. It's not going to choke. It's not going to say it doesn't compile. It's just going to say, I'm going to ignore this particular template. So t is not defined in the false case. That means the substitution will fail. Whatever it is you're trying to do, however you're trying to use type, it's not going to be defined. It's going to be an undefined type, quite literally. Right? But that's not going to stop the compiler. What it's going to do is it's just going to say the template is going to be removed from the overload set. So we're going to create this template on some enum, and what we're going to say is that the template is called enable bitmask operators, and by default, it's going to just return false. And it's going to do this. It's going to be evaluated const expert. It's going to be evaluated at compile time. Okay. By default, always false. It requires opt-in. We're going to have to explicitly say, I want to apply this. I want to enable bitmask operators on this enum. We will have to specialize this to stay true. Actually, we won't be doing that, but that's okay. This is a template function, not a template class. Why? Why did we choose a function instead of a class? You know, Steve? Oh, you know? Can you say that again? No, because all we're doing here, this by itself is not SFINAE. This is not that. This is just allowing us to be able to opt in so that when we create our own enums, we can specifically say, by the way, this enum should be a bit maskable enum. That's all it is. Yes. What's the advantage to overloading it? But couldn't you, if it was a type, couldn't you just do a specialization? Exactly. If this was a type, we could specialize it. We could say, I want to specialize this where E equals my enum that I want to be bit maskable. But if I did that, it would have to be in the same namespace as the original declaration. However, if I make it a function, I'm not specializing it, I am overloading it. We'll see how that's actually done later, but that's the key. That's why function instead of a template. All right, so this is the same code we had before for our or equals. I'm putting it back here because I'm about to do a transformation on it. Watch the E. I'm just going to put the E on its own line. Same code. I just wanted to put the E on its own line. Right? This is the same thing we did before. And now why did I do that? It's because I had to have a little room because now we're going to say something really long. But we're going to break it down. And it's going to make perfect sense. What is it going to say? Well, if you pull this out, we have this enable if. We talked about that before. Enable if takes two parameters. What's the first parameter? A compile time Boolean expression. Let's ignore that for now. What's the second parameter? Is the type, and in this case, it's the type, oops, this one. It's the type that we want to use if the expression is true. If the expression is false, there's no type at all. It just goes away, right? So what this is saying is that if this thing here is true, then the return value here is going to be E. And if this thing here is false, what is it then? Doesn't exist. And this particular function template just cannot be applied in the situation that we're trying to apply it in, which is some situation where it would have to be E as the parameters that are being passed. Okay? This is key. Does everybody understand what we've done here? Yes. I'm sorry? Yes? Well, first of all, this would be done at compile time. So it could be a runtime error. It would either be a compile time error or not. And in fact, this could be a compile time error. It would be a compile time error if there's no alternative, right? If there's some other function that takes these parameters, that function could still apply. So that's why it's saying it may not be a compile time error. All it means is that the compiler is supposed to close its eyes and pretend that this particular function was never declared in this particular case, right? Now, is there going to be some other function? No. We actually want a compile time error. We want that enums that are not bitmask operator enabled, we want them to not compile. That's really what we wanted, right? Or at least not apply in this specific case, right? So so we actually are probably going to get errors here because we want it to not compile. That's what we're looking for. All right, and then we have to repeat this again for all these different operators. We have to have 7 of these. But of course, we do this only once, right? We create this library of functions only once and can apply them to any enums we want to be bitmaskable. Did you have your hand up? It could in fact have been a type, but the advantage is, I'm going to show you in a minute where that would make a difference. And when we get there, we'll discuss it again. All right, so I am in my namespace now. Notice that this library of enums, this is in what namespace? What do we call this namespace? The bitmask namespace, for want of a better term. This is our library. But now I'm in the application space, and I'm in namespace user, right? And I'm about to define my enum. So I'm saying enum struct my bitmask, because this set of values are my enum that I would like to have bitmask operations applied to. Do we understand where we are here? Okay. We are assuming the library is done. Library only has to be done once. It can be complicated and ugly, and it can have things in it like enable if. We're willing to do that because we just assume those are written by Boost programmers, and we don't actually have to see that. Now we're users, and everything here has to make at least some level of sense, right? So, so what do we have to do to make my struct bitmaskable? I think this is shifted somehow. I'll have to fix that. But anyway, the idea is that, again, in order to make this work, these have to be bits, 1, 2, and 4. You know, the enum itself has to be a good bitmask candidate. But then we also say, oh, I'm going to write the const for bool enable bitmask operators for my bitmask, and that returns true, right? Remember before we said we wrote the templated one that returned false for anything. But now, is this a specialization? Is this a template specialization? No, this is just an overload. The compiler will always prefer my overload for my type. Even though the template will apply to everything else, but the template never applies to any situation where I have defined a template, a function. It's going to prefer mine. As long as it doesn't have to do a conversion, it's mine and it'll prefer that one, right? And so I have overloaded enable bitmask operations, my bitmask, to return true. So that's me telling the, opting in to enable bitmask operations. Notice, this is a function, so it will overload. If this had not been a function, if it had been a type, if it had been a template, class template instead of a function template, then I couldn't have overloaded it. You can't overload type template. You can, however, specialize type template. So I still could have made this work. But the problem is that when you specialize a type template, or even when you specialize a function template, but remember, this is not a specialization. If you specialize a function template or a type template, you have to specialize it in the same namespace where the original was created. So what that would mean is that I would have to end my namespace using here, and then I would have to open up namespace bitmask in order to specialize this guy. That's what I didn't want to do. So that's the answer to your question, why I preferred the function to the type. I could have used the type, but if I had, I would have had to specialize it in that bitmask namespace. And it turns out that I'm doing way more work than I'd like to do anyway, so I don't want to do that. Okay? What is this? What do you mean this? Yes, you can specialize the type, and that does work, but it requires being in the user namespace, right? So this allows us to use an overload instead of a specialization. All right, so this is overload and not a specialization. It could have been implemented as a class template, but that specialization would have had to been in the original name. That's what we, that little trick made this just a little bit easier to code for the user. All right, so we're going to use our enum struct. So we're going to include, here's our user HPP that has our enum in it. Here is our library, bitmask.hpp, that has all the templates that actually allow the bitfield operation. And of course, we need IO string. Fine. Okay, so int main, not inside a namespace. Can't be. And then what I do is I want to create A, which is my bitmask first, and B, which is my bitmask second. And I want to stream out what is A or B. And so I'm actually creating this integer from A or B and streaming it out. Does that work? Why not? I don't need the static cast because the whole point of my making these bitmasks is to support this. I'm not sure why. Why did I say that cast to an int? Oh, it has to be cast to an int, but this is an explicit cast. It's cast to an int just so it's printable. Enums are not ordinarily printable. So I'm explicitly casting this to an int in order to print it. But the question is, can I bitmask bitwise or A and B with this code? You're saying no. Why? Ah. So it won't compile, and the reason it won't compile, and again, somehow all my stuff is shifted over. It's supposed to be pointing here, but it's an invalid operation. There is no binary expression, my bitmask, my bitmask. And that's what we just went through all these hoops for, right? So how do we fix that? Well, what we're going to do is we're going to actually have to say, using bitmask operator or equal in my namespace where I declared my bitmask. Okay? And in fact, we're going to have to do this to pull the operator into the scope, because argument, what is it called? Argument dependent lookup is necessary, because what's going to happen is, let's go back to this code here. In this situation, the compiler is going to say, I don't see any function in this namespace that allows me to do A or B, because that function is defined in the bitmask namespace. But the interesting thing is the compiler has this special rule called argument-dependent lookup, because we don't want to call it Koenig lookup anymore. And what it does is it says, well, before I give up, I look in my current namespace, and I don't declare anything in my current namespace, right? This is main. You don't do anything in the current namespace. So it's not in any namespace, so that the functions that are in bitmask are not visible, and there's no function. But before giving up, the compiler makes this one last ditch attempt to find what we could make sense out of. And what it does is it says, I'm going to look in the namespace where all of the individual arguments are defined. So it's going to look up here, not in bitmask, but in user. Because my bitmask is defined in user. So it's going to look in that namespace and see, is there something in there that will let me do this bitwise OR? And will it find it? No, it wouldn't find it, but we're going to put it in there. So now we're going to put this in here. It's going to pull this operator, just saying using. We don't have to say what it does. We don't have to say anything about it. We just say using bitmask operator or equal. And what that does is it pulls this into this namespace. Yes? I think you're exactly right. We're going to have to pull them all in. Yes, you're right. Yeah. But I wanted to point out why, right? The reason is because the compiler has to know that these operators apply here, and we have to actually define them in this in the namespace where this is defined, except we don't actually have to define them there. We can tell the compiler, pretend like this guy is here. Use him in this namespace. Anything you do in this namespace, use this guy. Okay? Yeah, yeah. Yeah, I hate that's so this is a using declaration. What you're talking about is using directives. And I don't like using directives. I think they're kind of overkill. Although as I think about it, I'm kind of warming to it. And the reason is that the last thing I'm going to say about this whole thing is that here's what you need to do. We're not quite finished. This is kind of stealing my own conclusion here. This is what you need to do to create your struct bitmask, your bitmaskable enum. But notice almost all of this is just boilerplate, right? And in fact, except this little thing right here, the whole thing could be replaced by a macro. Oh, did I say that? You'll notice there's no such code in the deck. I couldn't make myself type the code. But this could be a really handy macro where we just say, you know, make this enumerable of type bitmask, and it generates all this code. But I would prefer an enum directive, I think, to a macro. So maybe that's a good enhancement. So I think the next version of slides, not only are we going to fix that terrible bug in the operator equal, but we're also going to, in the or equal, we'll also maybe use a using directive here. Okay? Thank you very much for that. I have a book for you. Come up here afterwards and I'll give you my book. Okay. So now that we've done this, now we can do our or equal. And notice what else we're doing. We're doing this. We're creating a C, which is a copy of A. And we're doing all this so that we can show the or, except, oh man, I didn't do the or equal. Well, you'll just have to, pretend it's an or equal instead of just an or. That's a typo too. The point was to demonstrate that both of these work. And then what is this demonstrating down here? I'm creating, it says int k, square bracket, static cast int a or b. What is the point of this? Yes. To demonstrate that that's context. Exactly right. Our output is identical to these guys, and this is actually doable at context, so that we can do these kinds of things. Yeah. Is that right? You're saying no. I don't think. Steve, can you do this? Yeah, I think there's a certain influential person on the standards committee who thinks that variable sized arrays are spawn of the devil, and he thinks that the most important contribution he's made to computing, that's what he said. I don't know, this is a paraphrase of what somebody told me he said, was that people no longer use arrays, they use vector instead. And he is dead set against it. I was told this story. All of the compiler implementers got together and made a proposal to the standards committee to standardize resizable arrays, because they all had to implement them for C. Because what is it, C90? What is it, C99? C99 put it in, and so everybody has to implement it. But for C++, they're all slightly different. And so they made a proposal to say, let's have a standard, and that got killed. And it's standardization of existing practice. It is exactly the mandate of the standards committee, but it got killed because the powers that be don't want us to use resizable arrays because they think that vector is much better. Okay, so I think that demonstrates context for. I may have to change my slide to do it a different way, but the idea is to demonstrate that happens at compile. So I want to thank Anthony Williams, who wrote the original article. I want to thank Louis Dion for showing how to pull the operators into scope, and Jay Miller for using a function overload rather than a template specialization. And I need to get your name so that I can add you to the list for the using direct. Anyway, anybody have questions? Yes. I don't know. I hadn't thought much about it. In general, I think the standard's pretty big, and if we can do something without putting it in the standard, this approach is not perfect, but it's usable. On the other hand, why stand in the way? Why make anybody jump through a hoop at all if you can make that not a hoop? It just adds another 20 pages to the standard, and when you're at 1,500 pages, who cares? I don't know. I hadn't thought about it too much. Bitmask what? Uh-huh. Mm-hmm. Oh, I see what you're saying. Oh. Okay, I think you're not saying what I thought you were saying, and I think what you're saying may be more interesting than what I thought you were saying, but I still don't think I really understand what you're saying. So, so next month, you can present present how that should be implemented, right? I don't mean to cut you off. It's just I really don't think I'm wrapping my head around what you're trying to say. But say it. Put it in a blog post or something like that. I have this blog that's all dusty, and if you wanted to post something on my blog, I'd be really happy. Anybody? I thought yes. Go time. I'll be the judge of that. So I'm unaware that the committee decided against that. And what I mean is, I'm not sure there was a proposal to do that. Was there a proposal to do that? I don't know. It's quite possible that the proposal to do that has your name on it and it just hasn't been written, right? Any other questions? Yes. Yes, yes. Uh-huh. Uh-huh. Yes. 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 If you want to do Enum Bitfields, you've already dealt with that issue, right? But usually, if you want to do Enum Bitfields, you're not using switches, right? Switches are for the non-Bitfield enums. If you're using Bitfields, then you're doing a bunch of masking to get at what the individual options were anyway. I mean, I think that's just how you'd have to use them. Any other questions? Well, you're either terribly tired or terribly bored, or I've beaten you into submission. Thank you all very much. I have a few copies of my book up here. So if anybody's dying to have me put my name in a book, I'm willing to do that. And you particularly should come up. Whoever made the suggestion about the directive,